SwayamPrabha. Digital India. Educated India.
Welcome. So we are in lecture 10. So we were doing in the last class the weak form, and in doing so we also defined the strong form. So, and we also solved some bar means problem. We have also considered bar problem where the weak form or the variational form or the weak statement or variational statement has been derived. So in doing so, we also defined the bilinear form and linear form, and we also defined what is the bilinear form and what is the linear form, how it's means what do we mean by bilinear form, and also we have defined symmetric bilinear form. So in this lecture essentially we will learn another method, that is Rayleigh-Ritz method. So first I will start with some of the previous things what we have learned. So let us have a small recap. So first what we have learned the strong form of a potential problem So potential means where the potential functional or potential energy functional in our mechanics sense is defined. So potential functional, and how we obtain it, this is nothing but the Euler-Lagrange equation. Okay, so we have done this. Now also when we have the Euler-Lagrange equation or the strong form of the system, then we defined how to construct its variational statement or weak statement. Right, now this is nothing but the weighted integral method. So weighted integral form of the strong form. So now while doing so we also did the integration by parts, so which essentially helps us. So important ingredient in it is the integration by parts, which has two consequences. First, it reduces the differentiability requirement, that is your if the strong form is second order, by integration by parts we transfer one of the differentiation to the weight function, which finally reduces the integrability or differentiability requirement of the field variable. So this is one of the advantage. So now second advantage is that it's automatically satisfied natural boundary condition. So natural boundary condition satisfied. So this is the advantage of integration by parts in the weak statement. Now while doing so we also defined the weak form of this form, that is B of V comma U equals to L of V. So now here U is the field variable and V is the weight function. Now this weight function has to be admissible. We cannot choose an arbitrary weight function because weight function, the admissibility condition for this weight function is that it has to satisfy the homogeneous boundary condition. So that's the weak form or the weak statement. So for instance, in case of a bar problem in the previous class, we have seen that is the bilinear form looks like this: 0 to L dv dx AE into du dx. So this is the bilinear form, and similarly the linear form is integral 0 to L if there is a distributed load Q0 V dx plus your boundary condition, that is V of L into P0. So that is the problem I am considering this. So there is a P0 force and there is an Q0. So this E is constant, A area and length L. So the boundary condition also we know. So here while doing so, we also found out that this bilinear form is symmetric. So what is the symmetricity means? That means if I change the argument of the bilinear form, that is B of V comma U must be equals to B of U comma V. So now this is the symmetric bilinear form. So if it is a symmetric bilinear form, then we can define the quadratic functional from the this thing. So how it is? So we can derive quadratic functional. So let us see how we can define quadratic functional. So for instance, if I take this bilinear form, that is B of V comma U, that is essentially 0 to L dv dx AE into du dx into dx. Now while defining this quadratic functional, if you have means in the previous lectures, you can have a very similarity that V is essentially variation of U. There is a similarity of variational first variation when we derive the first variation for the Euler-Lagrange equation. So it is nothing but the delta of U, that is variation of U. So if I substitute this thing here, so B is like this. If I substitute, then this is nothing but d of delta of U dx into AE du dx into dx. So now I can just use my this property of the delta operator, so which I can write du dx. So that is the commutative property with the differential operator. So now this is du dx. So now if this is a symmetric bilinear form, if it has to be symmetric bilinear form, then I can just take this delta outside and write this as AE by 2 into du dx whole square. So remember, if this is not a symmetric bilinear form, then essentially symmetric bilinear form means here, that is B of delta U comma U is essentially B of U comma delta U, right? So now if you don't have the symmetric bilinear form, then also we can define potential functional, but this is not the procedure we are doing it right now. So there is a possibility of doing that, but we'll leave this thing for right now, and then let us continue with this. With this we can have this essentially if I write my this thing, that is delta, I can write this is as b of u comma u. So this is my first term. Now the second term, that is the linear form, this is also I can write in this form, that is L of delta u, essentially 0 to L q0 delta u dx plus delta u of L and p0. So this we can also say that if I take the delta operator out from these two expression, so that is nothing but delta of L of u. So now if I write my weak statement, that is b of u comma or delta u comma u, which is equals to L of delta u. So this means that is b of delta u comma u minus L of delta u is 0. So this means that it is nothing but half of delta of b of u comma u minus L of u, right, delta of L of u. So this is equals to 0. Now I can take this delta operation delta operator out, and then I can write this is nothing but half of b of u u comma u minus L of u. So if you look carefully, this is nothing but the potential energy of the system. So that means if I have this bar, the potential energy expression for this bar can be easily written for this bar as this. So we know what is the potential energy. So for instance, the potential energy of this bar is integral 0 to L a by 2 into du dx whole square into dx minus integral 0 to L q0 u dx and your the boundary term, that is u at L into p0. So this is nothing but the work done. This part is nothing but the work done. So negative of work done, and this is the strain energy. So now if you look in this expression, that is, this is the same thing. So b of u is nothing but this quantity. So this quantity. Now I can say that this is the first variation of the potential energy. So if you have read that this thing, that minimum of potential energy theorem, then this is nothing but the minimization of the potential energy, or principle of energy, potential energy. But here it is interesting to note that this is a quadratic functional. So now this I will not elaborate much thing about the quadratic functional here. Rather, I will say that if this functional derivation of this functional is possible if the bilinear form is symmetric here. Now for what is the use of this? So use of this is, if you need to construct this potential energy of the functional, then we can find out that from the differential equation itself or the Euler-Lagrange equation itself, we can go back and find out the potential energy functional. But it is not necessary that potential functional will always exist. Now, I think we have discussed this in the last class. So, basically you have a functional, so potential energy functional, when you take its first variation, that is delta pi is 0, then you get its strong form that we have seen in the last class. So you get the strong form. Now when we take the strong form and construct its weak statement or the weak form, then rather we take the integral statement or weighted integral statement, then we get the weak form. So once we get the weak form, then again we can, if the weak form is symmetric and bilinear, then we can have this quadratic functional. So the requirement is symmetric bilinear form. So this, if satisfied, then I can construct it potential energy. So this is in nutshell what is the weak form. Now, so we constructed the weak form. For instance, let us also see the what is the weak form for a beam. So the beam problem we have did it earlier. So let us consider a simple beam. So let us consider a simply supported beam. So this is my simply supported beam. So this is, say, there is an UDL. So this UDL, let us say Q0, okay, and the boundary condition is W equals to W0 equals to 0 and dW dx, d2W by dx2, that is the moment here, is also 0. Now similar condition here, WL equals to 0 and EI d2W dx2 is equals to 0. Now in this case, what are the weak forms? So potential energy statement, potential energy expression we know, that is integral 0 to L EI by 2 d2W dx2 whole square dx, and then the this thing, the work done by the external force, that is Q0 into W dx. So there is no boundary term here because these terms are homogeneous. So forcing terms are homogeneous. So this is the potential energy. And what is its governing equation? Governing equation is, we know, that is EI d2 d to the power 4 W by dx to the power 4 equals to Q0, and along with the boundary condition, that is W0 equals to EI d2W dx2 at x equals to 0 is 0, and WL equals to EI d2W by dx2 at x equals to L is 0. So this is my governing equation. Now if I want to construct its weak statement, so this is the strong form. So now if I want to construct its weak statement, so simply I will write its bilinear form. So let us consider V as my weight function. So the bilinear form, if I do it, then it will be like this. So d2w, so d2v by dx2 into ei d2w dx2. So if you have seen this earlier, we have to do 2 times integration by parts, and L of v, that is the linear form, is nothing but this. So integral 0 to L q0 v dx. So here v is the weight function. So what is the requirement for v to be admissible? That v has to satisfy the homogeneous boundary condition. So that is at x equals to 0, it has to be 0, and x equals to L, it has to be 0. So that is the homogeneous boundary condition. So the weak form becomes this. So b of v comma w equals to L of v. Now, so this is an example. Now we'll define, so even if we have this weak form, so our objective is now how to solve this weak form. So one of the method is that you see how to approximate this problem, or how to solve or how to find out the solution of this problem. So to do that, one of the method I will discuss today, or I will start today, is the Rayleigh-Ritz method. So Rayleigh-Ritz method. So in the Rayleigh-Ritz method, before starting this Rayleigh-Ritz method, let us see how we can do it. So the main objective is here to find out the approximate solution of the problem. Even though the problems we are discussing can be solvable exactly, but our objective is to how to construct its approximate solution. As we know that we need not to have a approximate exact solution for all the problems involving complicated geometry and boundary conditions. So now if I want to approximate, let us consider the any potential problem. So let us consider u I want to approximate. So u of x, let us approximate in this way. Say j equals to 1 to n term approximation. So this is cj phi j. So phi j are functions of x, and obviously we may have a non-homogeneous boundary condition, so we also need something phi 0 of x. So that is important thing here. So now in doing so, if we substitute this approximation in the weak form, then we can find out and solve it. So I'll come to that. So before that, so what is this Cj? So Cj's are the constant. For instance, if I want to approximate ux with some function, so c1 phi 1 plus c2 phi 2, like this I can approximate. So these Cj's are known as the Ritz coefficient. So this is known as the Ritz coefficient. Now this so if I now put this thing in the weak form, let us consider our weak form is of this form. So let us consider our weak form is this v u equals to L of v. So now in the weak form, here we choose the weight function v. Now this v is essentially we have to choose v. So if I choose my v as phi I, so for I equals to 1 to n, then 1 to n, then what will be my weak form? So if I choose my v as same as this function. So also phi I needs to be admissible. So that we should always keep in mind. So that means if I substitute this v and u here, then my weak form will, the bilinear form will look like this. So phi I comma, now this is my I equals to 1 to n, then Cj phi j plus phi 0. So this is my weak form. So now here I will have phi I. So now you see that each I will results in a one linear equation here if the bilinear form is linear. So that means that bilinear form what we are doing is linear. So now this if I expand, so b of phi I comma summation of I equals to 1 to n Cj phi j equals to L of phi I minus b of phi I comma summation of phi 0 is this. So now I can simply write this. I can take this summation outside over j, so I can write j equals to, here it will be j equals to 1 to n. So j equals to 1 to n b of phi I phi j, and I can take Cj outside. So this will give me the linear equation what we are looking for. Now if you look carefully, that this term is mainly due to the non-homogeneous boundary condition. So if this term is non-homogeneous, means homogeneous boundary condition we have, then we'll have this term 0. So now this will result in simultaneous linear equation for I equals to 1 to n. This will leads to a linear system of equation, and we can solve this linear system of equation to find out Cj. So once we find out Cj, then we can obviously solve the problem and find out the approximation clearly. Now once we do that, then let us also discuss what is the phi 0. For instance, if you have a non-homogeneous boundary condition u equals to u0, then what will happen, u of x0, my approximation will be Cj phi j of x0. So j equals to 1 to n. So this is my given non-homogeneous boundary condition. So now this will be having phi 0 of x0. So naturally, if I take this thing, these quantities are 0. If I take these quantities as 0, then my phi 0 of x0 will be u0. So this has a advantage because I am using phi j phi as my weight function also. So and the weight function also has to satisfy the homogeneous boundary condition. So that in that way, if I choose this function is also at x equals to 0 0, then I can use this as a weight function. So naturally my phi j will be u0. So phi 0 will be u0. Now what I mean by this, that phi 0 of u0 is u0 means that it satisfies my approximation of ux always satisfy the inhomogeneous Dirichlet boundary condition or the kinematic boundary condition. So this way, if we can proceed, we can solve the problem. Now I will explain this thing in terms of a problem with a different I can explain it in terms of a problem, this thing more in detail. So before that, let us now investigate what happens if I get this linear system of equations. So one of the important thing of this linear, so if I write this thing for I equals to 1 to n, so what I will get, suppose I will get a matrix of B, so and then I will get a coefficient vector C, and there will be some right hand side F. So this equation naturally will have the size of B will be n, and this will be n term n cross 1, so this will be n cross 1. So now my B ij is essentially for the bar problem. So what will be the Bij? So for the bar problem it will be 0 to L d phi I dx A d phi j by dx into dx. So this is my Bij. So now this system of equation has to be invertible. So that means it has to be non-singular. So what it means by non-singular? That means that even if we invert this system of equation, then I can get the solution of C. So that means the non-singularity, how to ensure the non-singularity of this matrix B. So one of the condition is that first of all, that it has to be, so that means what is non-singularity condition? So it has to have the full rank. So that means it will lead to linearly independent columns or row vectors. So naturally this will be symmetric. If I choose phi I and phi j of same function, then it will be symmetric, and the bilinear form is also symmetric, so it will lead to symmetric matrix. So essentially this type of matrix is known as the stiffness matrix. We will learn it in the context of finite discretization in the later lectures. So now, so this will lead requirement of this, that linearly independent columns or rows. Okay, so that means it will lead to my full rank, so full rank matrix. So this is essential to invertibility. So this will lead to me full rank matrix. So how to ensure that? So that means my phi I phi j has to be linearly independent. So that means my weight functions phi i's has to be linearly independent. So how to choose linearly independent polynomials? For instance, 1, x, x squared. So these are these we can choose as a weight function. So second thing is that we always prefer to take the complete polynomial. What is the use of this complete polynomial? Because if we want to find out approximate solution, so that means we don't know the exact solution. So the solution, if I start with a, suppose I start with a quadratic solution, and then we don't consider the linear term, then what will happen, that if the solution is somewhere linear, the solution, our approximation cannot represent the linear solution. So the one of the requirement is that we should have a complete polynomial. And obviously my phi j's or phi i's at x0 has to satisfy the homogeneous boundary conditions. So these three are main requirement for this successful solution or the unique solution of CI's or CJ's. So I will means we can do a problem on this and then find out what is the solution. Now, so what kind of problem we'll choose? We'll choose a simple differential equation and a beam problem in the next class. So I stop here today. So in the next class, we'll do some problem on the Rayleigh-Ritz method and see how this knowledge, whatever we have learned till now, we can implement to find out some solution of the mechanics problem, right? So I stop here. Thank you.